Thank you. So I'm literally the only thing which is between you and the conference dinner. Just one more thing to eliminate. So first of all, I'd like to thank the organizers, Roland and David, can't see him, and Brigitte, for the opportunity to come here and to talk. I'm sad that we're already been here now for almost 3 weeks, and I'm sad that it's a sad week, that it's the last week. But it's very nice here, and I know that everyone is complaining about the weather, but for anyone who spent this time of year in Melbourne will know to appreciate the temperatures that we have here at the moment. Okay, so I want to talk about today about scattering problems, which are motivated by nonlinear wave equations. And I want to talk about work that I have done with Hans Lindblad. And what this is about, so I'm going to talk about scattering problems for wave equations. So I'm going to, for most of the talk, I'm going to consider scalar wave equations, and all of the, but much of what I'm going to say is applies to systems. It's you'll see. For simplicity, I'll talk about the scalar case, but everything I'll say is in dimensions 3+1, and this here is, if you like, the D'Alembertian in Minkowski space. And so what I'm interested in is scattering problems with homogeneous asymptotics. And what I mean by that is I'm interested in situations where solutions have homogeneous asymptotics, meaning that asymptotically, as t goes to infinity, the solution looks more and more like a homogeneous function of a certain degree. And so the notation that I'll use throughout, I mean by that, like when I write phi lambda, for example, I'm talking about functions which are homogeneous as functions on R3+1 of a certain degree. So here I mean of degree minus lambda. And so one way what that means is, for example, okay, if I say that, another way to understand what I'm talking about is if I have a homogeneous, if the solution looks like a homogeneous function of a certain degree, that means I can also, for example, write it as, if I take a to be minus t, the solution decays at a certain rate. It has a certain tail, 1 over t to the lambda, and what remains is a function on time-like lines. And so I will explain, of course, how that, I'll explain how I'll explain what, in what situation you might be for what situations you might have these type of asymptotics in a moment. So I'll have to explain why I'm interested in and where this is coming from. And then I have to explain what I mean by a scattering problem. And both of that I can explain maybe most easily with a Penrose diagram. It's this is a workshop in nonlinear waves and relativity, so I feel like I'm allowed to draw a Penrose diagram, even though, I don't know, I think, Jeremy, you didn't draw one today, so I'm literally the first one who's going to do it in this workshop. So I'm going to draw the Penrose diagram of Minkowski. Penrose, Minkowski. And this is what it looks like. And I have here future null infinity. This is, if you like, the endpoint of outgoing null geodesics. And so in this picture, it's quite easy to explain what I mean by a scattering problem. So Avi Sofa already gave us sort of an introduction to scattering problems, and he mentioned some of the historical origins of scattering. And I don't remember when I was a physics student, the first time I sort of encountered this was, for example, when people were trying to understand, say, the structure of a crystal or some solid. What you do is you send in a wave. So you have some object which has finite spatial extension. You send in a wave, and that wave gets scattered from the object and leads to an outgoing wave. And you're trying to understand, you're trying to learn something about the object from, if you like, the scattering map, which is future past null infinity. Which is, if you like, a scattering map. This would be a map from the incoming wave to the outgoing wave. That's sort of what it classically means. What I will talk, when I talk about scattering today, what I have in mind is the construction is more the construction for example, nonlinear equations from the outgoing state, from null infinity, to say the construction of the whole solution from scattering data at null infinity. And in particular, I'm interested, if you like, in the map from future null infinity to t equals 0. And so the one way of thinking, so what I'm describing here in these sort of classical situations, these homogeneous asymptotics do not occur, because one way, what I'm talking about here is, if you like, is if you have asymptotics towards what's called time-like infinity, non-trivial asymptotics towards time-like infinity. So in this Penrose diagram, all the time-like future-directed straight lines, in other words, the orbits of particles moving on straight lines, they all end up here at time-like infinity, and I'm interested in situations where you have that. So you could ask now, okay, why do you have it? So if you, for example, if you look at a nonlinear equation, well, let's say this depends on phi and the derivatives phi, and I was gonna think, and I want to understand, like, how does that, for example, look at a situation where I have stability around the trivial solution, and I was gonna think of, say, an iteration where, say, in the first case, I'm just gonna prove I'm gonna solve a linear equation, and that could be the case, for example, here, where that could be a solution which, for example, comes from compactly supported data, and it would really live only in this picture in what's called the wave zone. So in the wave zone. But you now have, for the next iterate, if you like, next iterate, you're looking at a wave equation which has a source which is not spatially of finite extent, but it goes all the way into the wave zone. And then from that picture, it's clear that the solution to that problem, which has a source in the wave zone, that's not gonna be supported in a region like that. It's not for that. Huygens principle is not gonna hold. You have a source which lives in the wave zone. The solution is not gonna be, which is computed, if you like, from the backward light cone, is not gonna be zero, and it is gonna have asymptotics towards time like infinity, and these kind of asymptotics that the kind of homogeneous asymptotics that I'm talking about here, they appear, for example, well, for all equations for which you have, so for example, for which a small data global existence, so for example, for equations satisfying the null condition and equations satisfying the weak null condition. And this is what certainly motivated us in the first place to look at that. Now, and I'll make this more precise in a second. We'll see how that what kind of I'll make more precise how these homogeneous solutions are related to the nonlinear problems I'm talking about here. But this is not the only case in which you are going to have homogeneous asymptotics. There's, for example, a recent paper of Jonathan and Sungjin, which discuss the appearance of these tails. In particular, what I'm interested in here is, if you like, the case, well, I mean, I'm going to be interested in the case 1 and 2. But these type of tails appear in many problems, in particular when you look at curvature perturbations, or when you look at wave equations on not on flat but on curved spacetimes, and these kind of tails are going to appear. Now, and I'll continue to say why this is so important for scattering theory, or why or the difficulties that it introduces scattering theory. But also, as a side remark, I should say that this type of homogeneous asymptotics here, they don't just appear for wave equations, but for example, they appear for kinetic equations. We've seen an example this morning in the talk of Alex of laws of Poisson. So, for example, there are scattering results, which, in particular, are for solutions which have homogeneous asymptotics. That's for example, the result of Ionesco, Calzada, Wang, and Wittmeyer. And I've recently made a contribution together with Martin Taylor on the scattering problem for laws of Poisson, which is sort of in the philosophy, follows the philosophy of today's approach, but it is somewhat a different problem, because the scattering data is free, and what I want to explain is that so there's a non-relativistic problem, there's no radiation. What I want to explain is that in the presence of for wave equations, when you have a radiative aspect, they're gonna the scattering problem is non-trivial, because it's not a priori clear what part of the scattering data is free to prescribe, and they're so-called matching conditions. So let me give you an example just to explain that straight away. So if you So let's say we are in a setting where we have a homogeneous degree -2 solution in the interior. So by interior, I also mean the interior of the light cone, or equivalently at I+, if you like. So let's say let's consider the case where you have a homogeneous degree -2 solution, which looks like this. This is a homogeneous type of homogeneous asymptotics that appears, for example, for equations satisfying the null condition. So, say I want to think of a setting where we have asymptotics like this. And on the other hand, you and on the other hand, you want to talk about solutions which have a radiation field. Also, that notion I'll make more precise in a moment. But in some sense, you should think. Let's say we are in a situation where we also want to, where we have the sort of the type of asymptotics towards null infinity that we have for the free equation. So we have a radiation field exists. Say G0. So in other words, if I have asymptotics, this is for, if you like, r minus t constant, right? So in this picture, let's say I have towards null. So in the wave zone, towards null infinity, that means these lines are where r minus t is constant. Okay, I call omega x over x. And you would have, what I mean is that as r goes to infinity along these constants, you want to have a radiation field. So now I'll explain that in a moment. You want to have a situation where you have a radiation field, but you also have this homogeneous solution at I plus, then you're going to see that there is a matching condition. So meaning that in these situations you see, because there is a point, if you like, I have two asymptotic regimes, one towards I plus, we have a radiation field, and I have another one at time like infinity. But there is a place where these two asymptotic regimes, they meet, and there they have to match. And that implies, since this is like let's call this 2m maybe, then we have like, this is like 2r over r minus, or t minus r maybe. Then you see, you're going to get the radiation field that is going to appear, function of q and omega, the 1 over q tail, or the 1 over r minus t tail, if you like, is not free. So in other words, there's a relation between the asymptotics of the radiation field and the interior solution. And if I were to solve the problem that I talked about, maybe a scattering problem, then I see for this type of equation, it's necessarily an interior solution. So it's not the whole radiation field which is free, but only part of it. And part of our work is, in all these problems, is characterizing, if you like, which part of the scattering data is free. Does it make sense? Sorry? What is the what? The other part? This one. It's there. It's just it's let's say if you look at solutions satisfying the null condition, you're gonna have as x over t is constant this type of asymptotics, and it's there. If you want to construct the solution backwards, it's there, and that gives a matching condition on the radiation field. This is part of the answer for in your this is. Yes. Of course, these are all. No. I'm saying this is an example for the of a case with homogeneous degree -2 asymptotics. I'm saying it occurs for all equations satisfying the null condition, and this is the basic upshot already. That I haven't explained how they come about. I'm just telling you it is like that, and the reason scattering with homogeneous asymptotics is difficult or interesting, if you like, is because you see immediately when there is a non-trivial star at I plus, there are matching conditions, which restricts the choice of the scattering data. Okay. So so what I want to do is let me what I want to explain is so I've talked about sort of motivated that this type of asymptotics occurs for nonlinear equations, and that's certainly was certainly our starting point. And I said it also occurs if you look at wave equations on a curved background. And in all these cases, it appears these tails, these homogeneous asymptotics appear even if the initial data is, say, compactly supported. And, but there is another reason that these homogeneous asymptotics may occur, and that occurs even for linear equations. And that is the case of when the initial data decays very slowly. And I kind of want to focus on that aspect, on that part of the story here today in the lecture, because it has very wide applicability. So essentially, in every equation in mathematical physics where initial data contains mass terms, you're looking at wave equations, that type of problem is going to come up. So, or it's going to be relevant. And what we have done there is, I think, genuinely new, and so I want to explain it. So this is the case of slowly decaying data. So roughly speaking, the setting is simply now the linear equation. But let's say you look at data which falls off, initial data at t equals 0, that only falls off like 1 over r, and the time derivative falls off only like 1 over r squared. Then in these settings, the solution is going to have different asymptotics in the wave zone than this. It's going to have logarithmic terms in it in general. And in general, it's going to have a homogeneous degree minus 1 asymptotics in the interior. So meaning, in general, in this setting, the solution has homogeneous degree minus 1 asymptotics. That means it only falls off like 1 over t in general. And the scattering problem in this case is one that we've completely resolved, and I want to explain it. And it's relevant in many settings. So, for example, what we've solved in particular is if you think of, I talked about scattering, if you like, from future null infinity to the data, but equivalently I can think of from past null infinity to the data. So if you think of what we've done in particular is we've characterized, if you like, all solutions to the linear equation. We've characterized, if you like, the scattering data at past null infinity that gives rise to solutions which only falls off like 1 over r. And that means like we've characterized what the data at past null infinity is like that gives rise to a mass term or a charge term. So let me explain how that goes. So so let's take this that problem head on, and let me look at data which is exactly homogeneous, and let me restrict, if you like, to what I call also the exterior of the cone. So this is the cone in Minkowski space. That's the exterior of the cone. And I'm posing data at t equals 0, which is homogeneous of degree minus 1. Then, so this is the case, like this. Then you can, so this is for r positive, right? And you can see, so this is, if you like, write it like this, at 0 r omega, 0 r omega. Can't be any more explicit, okay? So you can easily see that the solution to this initial value problem is homogeneous degree minus 1. Right? Simply by commutations, for example, with the scaling. And then, and now I can, so if it's homogeneous degree -1, which means that that means the solution to this problem is really just a solution on lines. I mean, it's the function. The solution is a function on lines, right? It's homogeneous of a certain degree. Now, I can. So this is, if you like, where x over t or r over t is constant, and I can consider the limit as r over t goes to 1. That means I'm oh, I'm going, okay. And I can do that. And I can, if you like, and I can compute that, I can compute what the solution to this initial value problem is. And we've done that. But I'm realizing as I'm speaking this, I kind of, before I wanted to go there, before I tell you about the solution to this problem, I actually wanted to take a little detour to the case of fast decaying data. That makes sense. So then it will be easier to understand what I'm saying here. So let me do that first. You'll see the significance of that a little bit better in a second. So one step back. Let me just one step back for 1 second. And that is, I quickly wanted to talk, before I continue with that, look at the case of fast decaying data, because that's the case that's really known. And so if you look at fast decay, so the analog of that problem, fast decaying data, which is something we all know. So if you look at the linear equation and you look at data which is, say, Schwarz, right? So for F and G Schwarz 3, then what I wanted to make precise is first the notion of the Friedlander radiation field. So in this setting, we know that we have data at t equals 0. We know that the solution lives in the wave zone, if you like, and falls off there like 1 over r. So I can define what's called the Friedlander radiation field, which is, I'm looking at the solution, it falls off like 1 over r, and I'm going out on one of these lines, which is, I'm fixing q equal to, say, r minus t, right? And a direction. I'm fixing a null ray, in other words. And I'm evaluating the solution at t, which is r minus q, and r omega, and I'm taking the limit as r goes to infinity. And that's called the Friedlander radiation field. And it's a quantity that lives at future null infinity at this cylinder here, right? And the point is that in the fast decaying case, there's a well-known formula which expresses the radiation field in terms of the radon transform of the data. So the radon transform, and then let's say the derivative of the radon transform of the other part. Okay. To an omega. And by that I mean, so this here is, oh, did I erase it? So, so this here is the radon transform, which is so radon, and that is an integral over planes. Right, and it is invertible. So this is, if you like, the simplest case of and where the two parts, you can think of this as a decomposition into an even part and an odd part. So what this formula tells you is immediately, if you like, the solution of the scattering problem that I talked about in the fast decaying case. Given a radiation field, decompose into even odd parts, use the invertibility of the radon transform, and I know what the data is. Now, this, however, is you see, the radon transform is an integral over planes, and for that applies only for that I need that the data is fast decaying, right? Otherwise, this is not even defined. So. And it's exactly this case here, which is at that border line where this doesn't exist. In other words, the radiation field as described up there doesn't exist. Now, there's one other comment that I want to make, is that you see here for the scattering problem. So in other words, the question of reconstructing the data from the radiation field, I see that there is what I call a compatibility condition. And that is, you see here, if I'm in the case of fastly decaying data, I can integrate this relation from minus infinity to plus infinity. And if I do that, this integrates to 0, and this here becomes the integral over these radon transfer integral over planes, versus the integral over R3 of G, right? And that in general is non-zero, but more importantly, it's independent of the angles. Independent of angles. Okay? So that means that you see here, if you want to talk about the type of radiation field that gives rise to a fast decaying data, there is obviously a condition, namely that F0 can't just be anything. It has, after integrating, it has to be independent of the angles. Right? And what we have done is we have generalized this kind of condition that follows from this representation formula, both to nonlinear equations and to the case of slowly decaying data. So let me return to this, and you'll see why I did this detour. It's we now know that if I'm in the case of this data, the radiation field doesn't exist, and you can guess there's going to be a logarithmic divergence in here if this is just like 1 over y squared, like there. And indeed, so let's call this a lemma. But nonetheless, you can just compute what the solution to this problem is, and I can take the limit as r over t. I know that the solution is homogeneous degree minus 1. Oh, let's call it this. The solution is homogeneous degree minus 1, so it goes like 1 over r. But as I'm taking this limit as r goes to 1, that's not going to exist, because otherwise I would have a radiation field. But there is going to be a logarithmic divergence in it, and that looks like this, which one can compute. And then the rest is a function of the angles. And that function of the angles is, what appears here is the so-called Funk transform. And the Funk transform is the analog of the radon transform on spheres. So here I'm integrating over planes. For the Funk transform, it's a transformation from functions on the sphere to functions on the sphere. So I have here my S2. I have an omega. The new function is I obtain by integrating over the great circle. So Fn, this here, is equal to 1 over 2 pi. The integral sigma omega equal to 0. I'm integrating over the great circle orthogonal to omega. Okay? And you see now, okay, that this is, so Funk was a contemporary of Radon, and he in his paper, on his thesis, he established, well, first of all, you see that this function is not quite directly Radon transform because it has a kernel. If you have an odd function, it's going to get annihilated. But as a function from, as a transformation from even to even functions, it is a bijection. And that sort of statement was, for example, studied by Helgason. And that we knew that is sort of classical. Now this transformation here is dismissively called by some the Gang transform. And it is also like a Funk transform. You can view it as a Funk transform of a one form, and was, for example, studied by Güleman. Now, nonetheless, it's not like that I have a, so what I want is kind of like an analog over here, like that the radiation field determines the data. It's not the case that this leading order term here determines m and n, because you see in the image of that are only even functions of n, an odd function. So even this is the image is an even function, the image of that is an odd function. So the odd part of n and the even part of m are not determined yet. So one has to go a little bit further, and let me write the next term. So I can just compute the next term. Although a bit unusual, I'm going to continue with that line above. So there's, if you like, a 1 over r term. Oh, and yeah, I have to write it separately anyway. Is that if you look at the parts that are not determined yet. So if I look, for example, here at the case, what did I say when n is, so for example, m is 0, but n is odd. Then you're gonna, then this logarithmic term is not there, and the solution is just gonna have look like this, where what comes up is a certain transformation of n, which is a non-local transformation, which involves an integral from -1 to 1 over averages, not over great circles, but all the other circles. So in other words, it involves an integral over these kind of circles. And if you look at the case when n is 0, but m is even, you're also going to find a formula like this after some computation, and that is going to look like this, where this mi is computed or defined like this. So when we came across these formulas, I had a hard time trying to understand why they're invertible, but after some, it's really the first time that it happened to me that I had concrete problems of 4 transformations that I didn't know how they related. And eventually I found a paper where all of these 4s are treated in one uniform way, and that is a paper by Mike Eastwood, who is enjoying life in the Adelaide Hills, and then there is Rod Gover, who is in Auckland, and Lionel Mason in Oxford. So what you have here is sort of a bit of Oxford Twister Penrose school, and they have looked at these transformations actually not in the setting of scattering theory, even though they have all worked on scattering theory, but from this paper it follows that exactly these 4 transformations that are coming up are invertible. So this transformation here, S, turns out to be the inverse of the Gang transform, and this transformation here turns out to be the inverse of the Funk transform. And what that means is that leads to a theorem that if you, which is sort of the analog of that for slowly decaying data, that if you have all homogeneous degree -1 functions are determined from, in the exterior, are determined from the first 2 terms in the expansion. So if you have a homogeneous degree minus 1 function as r over t, so this whole thing was for r over t going to 1. If you have a homogeneous degree function has an expansion, if you know these two functions, m and n are determined. You have a bijection between these two functions and m and n. So the picture that is sort of emerging is the following. If you so I drew a lot of Penrose diagrams, but somehow when I talk about homogeneous solutions, it's really a different picture that is relevant, and that is more the picture of that's more common in sort of the Melrose School of Microlocal Analysis, which is it's the radial compactification of Minkowski space. So in other words, if you look at R3 plus 1, and you do not distinguish null lines, but you just introduce a radius, if you like, which doesn't distinguish. It's just a radial variable on R4, and you compactify it, then you get a circle, and on that circle, and the cone looks like this. Now, the cone sort of splits up that sphere at infinity in two parts. So there is a sort of the sphere take away these two caps here and here, and that is all of, if you like, space-like infinity, because in this picture, what I have not all the straight lines through the origin, they remain untouched if I use this variable. So they remain straight lines. So all of space-like infinity is this. And this is where you should think these homogeneous degree minus 1 functions live that I have sort of characterized in this theorem. And in fact, any homogeneous degree minus lambda function lives here in the exterior of the cone. I've also talked initially about functions in the interior, which are functions which you should think of. They live on the cone. They live on this cap. Okay, they live on these caps. This is if you like all of I plus, and this is where the homogeneous homogeneous functions in the interior live. And what I have done here is I've given you a characterization of the homogeneous degree minus 1 functions. There's a similar analog. There's an analog theorem for homogeneous degree minus 2 functions, right? So lambda minus 2 or lambda 2, and then there is a story. Then we have homogeneous degree minus 1 and minus 2 functions in the interior. You've seen one example of a homogeneous degree minus 1 function, a 2 function in the interior. Now, but what is going on now? So you can view this now in several different ways. You can say, okay, I want to construct a solution which has exterior homogeneous asymptotics. Or you can ask, I want to construct one which has interior homogeneous asymptotics, or maybe both, and how they are related. So it turns out that these two asymptotic regimes, they are not independent. If you have one, then you have the other, and that in general, and that's mediated through the equation. But on the other hand, if you say, okay, but originally I wanted to solve the scattering problem. So if you want to solve the scattering problem, then you want to talk about data at null infinity, which is over there. So in this picture, you can, in this picture, like our time-like curves, which all ended up at time-like infinity through these ways. In this picture, it's now the null lines which end up at this point. And I can blow it up on this side and on this side. And it's here where the scattering data lies. So another way of saying is if I want to prescribe scattering data at null infinity, which has logarithmic terms and which doesn't decay, that will lead necessarily to a homogeneous function in the exterior, and it will be mediated through that theorem, because you can sort of think of the functions or part of the scattering data which does not decay to be related to these limits, which then in turn give rise to a function which is only degree -1 or -2 out here. Okay, so what I wanted to do now is give you the simplest example of a theorem, namely for the homogeneous solution, where you have both interior and exterior asymptotics determined from data at the radiation field. But I'm realizing I'm very slow. Should I finish? I should finish. Okay, then let me just say it in one word. So the theorem is, that was the word. The theorem is that there exist solutions to the wave equation which have asymptotics in the wave zone, which look like this. So in other words, there is a term, so r minus t and omega. So there are solutions to the homogeneous wave equation, which in the wave zone look like this. In other words, they don't have a radiation field in the classical sense because there's a leading order logarithmic term. And that function here, it turns out, is not a function of r minus t, but it's just a function of the angles. That's because we're looking at homogeneous at solutions to the linear wave equation. And that function is completely free to choose. If I choose that function, together with a function with the radiation field that does not decay, I can think of this, I'm constructing a solution for which I have a mass. And which mass is determined through these transformations. And the moment I have this logarithmic term, the moment this function is some non-zero function, I also have a function in the interior. And the solution in the interior is completely determined from that function on the sphere, which as a consequence, it has the consequence that also the limit of the radiation field towards the other endpoint is not free. So meaning if you prescribe the logarithmic term, then the limit in both directions is fixed. That determines, if you like, that determines the homogeneous degree -1 function here and here. And moreover, the radiation field does have different limits in this and in this direction. And if I were to spell out the theorem, it would characterize the remaining part of the radiation field that is free to choose. Then there are, if you like, this is really the simplest theorem of this theorem. Then you can have theorems for nonlinear or for nonlinear equation or equations with source terms where these effects add up. You have interior solutions which simply come from sources in the wave zone. They're connected to solutions in the exterior. Anyway, it's a bit of a story. I try to give the simplest version, and that's it. Thank you.